Somewhere beneath your ribs, in the quiet dark of your own body, something is working right now, and you did not ask it to, and you do not need to check on it. It has been working since before you were born, and it will keep working while you fall asleep tonight, patient and unbothered by whether you are paying attention. You could forget it existed for the rest of your life, and it would not mind. It would simply continue, the way a river continues, the way weather continues, without a manager, without a meeting, without anyone standing over it with a clipboard making sure it happens correctly. This is the process of digestion, and it is one of the strangest and most reassuring things about being alive, because it asks nothing of you. You do not have to remember to do it. You do not have to think your stomach into producing acid, or your intestines into contracting, or your liver into making the substances it makes. Somewhere, long before recorded history, before anyone had a word for stomach or bile or enzyme, human bodies were already doing this perfectly well, generation after generation, without a single person understanding how. And tonight, lying wherever you are lying, warm under whatever you are warm under, your body is still doing it. It doesn't need your help. It never did. I want to say that clearly at the start, because this is going to be a long, slow journey through the entire digestive system, from one end to the other. And if at any point it starts to feel like a lot of information, like something you should be memorizing, I want you to let that feeling go. You are not being tested on this. There will be no quiz about the small intestine. You can let your mind drift in and out, catch a phrase here, lose a sentence there, and none of it matters, because the actual digestion happening inside you right now does not depend on you understanding it. In fact, it seems to work best when you're not thinking about it at all, which is sort of the whole point of this recording. We're going to talk about the same tireless, quiet system that lets you drift into sleep without effort. So if your attention slips, if you stop following the words and just hear a calm voice describing warm, dark, slow things happening inside a body, that's not a failure. That's actually the goal. So let's begin gently, the way the digestive system itself begins gently, because nothing about digestion is sudden. There is no moment where a switch flips and suddenly food becomes energy. Instead, there is a long, unhurried sequence, a kind of conveyor belt that runs for about 30 feet if you were to stretch it out, though of course, inside you, it's folded and coiled and tucked away so efficiently that most of it fits inside a space smaller than a shoebox. That's one of the quietly astonishing things about the body. The sheer amount of tubing packed into so small a volume, folded over on itself again and again, like a hose, coiled neatly in a garage, taking up almost no room at all until you need every inch of it. This whole system, from your mouth to the other end, is really just one continuous tube. It might not feel that way, because we give the different parts different names, mouth and throat and stomach and intestine, as though they were separate rooms in a house. But if you could see it laid bare, you would see that it's all one connected pathway, an unbroken tunnel that runs through the middle of you, with different sections doing different jobs the way different rooms in a factory might handle different stages of building something. What travels down that tunnel enters as something recognizable. A sandwich, a spoonful of soup, a slice of fruit, and leaves, eventually having been broken down so completely that almost nothing recognizable remains. Along the way, it will be crushed, dissolved, soaked in acid, bathed in enzymes, squeezed by muscle, and slowly, patiently, taken apart into pieces small enough for your body to actually use. And this is worth sitting with for a moment, because it's a strange thing when you think about it slowly enough. The apple you ate at lunch, the bread, the rice, None of it can be used by your body in the form you ate it. A muscle cell in your leg has no use for a bite of toast. It has no way to accept something that large, that complicated, that stubbornly itself. Before your body can use anything you eat, it first has to become something else entirely. It has to be broken down into pieces so small they're almost not recognizable as food anymore. Sugars small enough to slip into a bloodstream, fats broken into fragments that can be carried and stored, proteins unraveled back down into their basic building blocks. Digestion, at its heart, is really just this slow unmaking, taking something whole and turning it into something small enough to disappear into you. It happens in two different ways, working together the whole time, like two different tools used on the same piece of wood. There is the mechanical side of digestion, which is really just movement, chewing, squeezing, churning, the physical crushing and mixing of food, not so different from what a mortar and pestle does, or what happens when you knead dough with your hands. And there is the chemical side, which is quieter and less visible, involving specialized substances that reach into food at a molecular level and cut it apart, snip by snip, using tools your body has been manufacturing since before you took your first breath. Neither of these processes could do the job alone. Chewing alone would leave you with very small pieces of food that were still, chemically speaking, entirely unchanged, still too complicated for your cells to use. And chemical digestion alone, without any mechanical breakdown first, would be like trying to dissolve a whole apple instead of a chopped one, technically possible eventually, but achingly slow, and not how your body chooses to do things. So the two work in tandem, mechanical and chemical, again and again, at every stage of the journey. Chew, then chemically alter. Squeeze and mix, then chemically alter again. Each section of the tube adds its own combination of physical movement and chemical transformation, so that by the time anything reaches the far end of the journey, it has been worked over more times than you could count, by more different processes than most of us ever learn about, all without a single conscious decision on our part. What I find most calming about all of this, and part of why I wanted to spend an entire long, slow recording walking through it, is that none of it requires effort from you in the way that effort usually feels. You don't tense a muscle to make your stomach churn. You don't concentrate to release the right enzyme at the right moment. Somewhere behind the scenes, timing systems are already handling that. Chemical signals passing quietly from one organ to another, coordinating a rhythm that has been refined, not over your lifetime, but over the entire span of human existence, and further back than that, through the almost unimaginable stretch of time before humans existed at all, when other creatures were slowly working out, generation by generation, the best way to turn food into life. You are the current, temporary owner of a system that has been tested and adjusted for an extraordinarily long time. And tonight, all of that inheritance is simply doing its work, unhurried, unsupervised, asking nothing of you except, perhaps, that you let yourself rest while it continues. So let's follow that tunnel from its very beginning. Let's go slowly, the way the body itself goes slowly, and start where digestion actually starts. Not in the stomach, as most people assume, but somewhere much earlier, much smaller, and much closer to the surface than you might expect. Digestion begins, in a very real sense, before there is any food in front of you at all. It begins with a thought, or a memory, or simply a smell drifting in from another room. Somewhere a pan is heating oil, or bread is turning golden in an oven, and the molecules responsible for that smell, tiny, volatile, drifting things, so small you'd need extraordinary magnification to ever see one, rise into the air and travel, entirely, by accident of physics, toward your nose. There, high inside each nostril, they meet a patch of tissue no larger than a postage stamp, dense with receptors, each one shaped to catch a particular kind of molecule, the way a lock is shaped to catch a particular key. That signal travels a remarkably short distance, all things considered, up into the olfactory bulb, and from there almost directly into structures involved in memory and emotion, which is part of why a smell can summon a childhood kitchen so much faster and more completely than a photograph ever could. But smell alone is not usually what starts the process moving. It's smell combined with expectation. Your brain, drawing on years of accumulated experience, recognizes the pattern. This smell has, in the past, reliably preceded food, and food has reliably been good, or at least useful, and it begins issuing instructions accordingly, long before a single bite has been taken. This is sometimes called the cephalic phase of digestion, a name that simply means the head phase, and it is worth pausing on, because it tells you something important. Your body doesn't wait for proof. It acts on prediction. Saliva begins to gather in the mouth. The stomach, sitting quietly in the upper abdomen, begins to secrete a small amount of acid in anticipation, and gentle muscular ripples move through its walls, as if warming up before the main performance. None of this requires you to have seen or smelled or thought about anything in particular. It's simply how a system that has spent an unfathomably long time learning to anticipate food chooses to prepare for it. Sight does something similar. The look of a plate, its colors, the steam rising off it, the particular sheen of oil on a piece of bread. These are processed by the visual system and then passed along, again, to structures that translate "this looks like food" into hormonal and neural signals. Even the sound of food matters, more than people usually realize. The crunch of something crisp, transmitted partly through the air and partly through the bones of your own skull as you chew, tells your brain something about texture and freshness that your eyes and nose cannot fully convey. Food scientists have spent careers studying this, the particular frequency range of a satisfying crunch, the way silence in a bite can make something feel stale even if it isn't, because the ears, it turns out, are quietly involved in eating long before you'd think to credit them. All of this, smell, sight, sound, memory, expectation, converges on one small, unglamorous, endlessly busy organ, the mouth. And once food actually arrives there, an entirely different set of processes begins, ones that are mechanical as much as chemical, and worth walking through slowly, because most of us do this several times a day without ever once considering what an intricate piece of engineering a bite of food is being subjected to. Start with the teeth, because they do the first and most obvious work. Human teeth are not identical to one another, and their differences tell a story about function. At the front sit the incisors, thin and blade-like, shaped for shearing, the kind of clean, decisive cut you use when you bite into an apple or tear a piece of bread. Just beside them are the canines, more pointed, better suited to gripping and tearing, a shape inherited from ancestors for whom tearing flesh or fibrous plant material was a regular necessity. Further back come the premolars and molars, broader and flatter, with irregular ridged surfaces designed not to cut but to crush and grind, the way a mortar grinds against a pestle. When you chew, you're not using one kind of force but several in sequence, a bite from the front, a tear if the food resists, and then a rhythmic, almost circular grinding motion at the back, powered by some of the strongest muscles, pound for pound, in the entire human body. The masseter muscle, running along the jaw, can generate an extraordinary amount of force relative to its size, though in practice, we use only a small fraction of what it's capable of, saving the rest, evolutionarily speaking, for foods far tougher than anything most of us encounter at a modern dinner table. While the teeth are doing this mechanical work, the tongue is doing something almost choreographic, constantly repositioning the food, sweeping it from one side of the mouth to the other, testing texture, keeping it away from the space between the teeth where it might simply sit ungrounded. The tongue is, weight for weight, one of the most muscular structures in the human body, composed of 8 distinct muscles working in combinations so fluid that we rarely notice the tongue is doing anything at all. In the same way, we rarely notice our own breathing until something calls attention to it. And layered across its surface are the taste buds, several thousand of them, clustered mostly along the edges and back, each one a small cluster of receptor cells capable of detecting only a handful of basic taste qualities: sweetness, saltiness, sourness, bitterness, and the savory quality known as umami, first formally described by a Japanese chemist in the early 20th century after he isolated the compound responsible for it. Everything more complicated than these basic qualities, the specific taste of a strawberry, the particular character of a good cup of coffee, is actually being assembled largely by the sense of smell, perceived from inside the mouth as food is warmed and released into vapor with each chew, which is part of why food tastes so strangely muted when a head cold blocks the nose. Saliva, meanwhile, is doing quieter but no less important work. It arrives from 3 major pairs of glands positioned around the jaw and under the tongue, and it is far more than simple water. It contains an enzyme called amylase, which begins breaking down starches, the long chains of glucose found in bread, rice, and potatoes, into shorter, sweeter fragments, right there in the mouth, before swallowing has even occurred. This is why a piece of plain bread, chewed for an unusually long time, will sometimes begin to taste faintly sweet, an effect you can test for yourself if curiosity ever strikes at an odd hour. Saliva also moistens and binds the chewed food into a soft, cohesive mass, known, rather plainly, as a bolus, and it lubricates the whole mouth and throat so that swallowing can happen smoothly rather than as a series of small frictions. Chewing itself continues until the brain, monitoring texture through nerve endings in the jaw and mouth, judges the bolus ready, smooth enough, moist enough, small enough, a decision made almost entirely without conscious involvement, the way you don't consciously decide when a sentence you're reading has been understood. And then comes swallowing, which looks simple from the outside and is, in fact, one of the most tightly coordinated sequences of movement anywhere in the human body, involving more than 20 separate muscles firing in careful order over the span of well under a second. The tongue presses upward and back against the roof of the mouth, pushing the bolus toward the throat. At almost the same instant, the soft palate lifts to seal off the nasal cavity so that food and drink don't drift upward into the nose, an event most people have experienced at least once, usually while laughing at an inopportune moment. And then comes the part of the process that quietly solves one of the body's more elegant design problems. The airway and the food passage share a single junction at the back of the throat, and something has to decide, instant by instant, which direction each swallow should travel. That junction is guarded by a small flap of cartilage called the epiglottis, which tips backward and down at the exact moment of swallowing, covering the entrance to the windpipe the way a trapdoor swings shut over a stairwell. At the same time, the vocal cords themselves draw together, adding a second layer of protection, and the entire larynx, the voice box, rises briefly upward and forward, tucking itself almost under the base of the tongue. You can feel this if you rest 2 fingers gently against the front of your throat and swallow slowly. There is a distinct rise and fall, a small mechanical journey happening just beneath the skin, one you have performed many thousands of times without ever noticing it as an event at all. For that fraction of a second, breathing simply stops. It has to. The two functions cannot happen at once, and the body handles this ancient scheduling conflict with a briskness that borders on elegant. Once the bolus clears the epiglottis, it enters the esophagus, a muscular tube roughly the width of a thumb, and, in most adults, somewhere between 9 and 11 inches long, running from the base of the throat down through the chest, behind the heart, before reaching the stomach just below the diaphragm. And here is where a small correction is worth making, because it is one of the more persistent misunderstandings about the body. Food does not fall down the esophagus by gravity, even though it certainly feels that way, and even though the arrangement of head above stomach makes gravity seem like the obvious explanation. If you swallow while lying flat on your back, or even upside down, astronauts have tested this quite literally in orbit, food still makes its way to the stomach, just as reliably as it would sitting upright. The real mechanism is a traveling wave of muscular contraction called peristalsis, and it is worth sitting with that word for a moment, because the process it describes shows up again and again throughout the digestive tract, in one form or another, all the way to the end. Picture the esophagus not as a rigid pipe, but as something closer to a long, flexible sleeve, ringed along its length by circular muscle fibers. When the bolus arrives at the top, the muscles just above and behind it contract, squeezing shut, while the muscles just ahead of it relax and open. The effect is a narrowing band that rolls steadily downward, the way a wave rolls along the surface of a rope if you snap one end, or the way you might squeeze the last bit of toothpaste from a tube by pressing your fingers just behind the toothpaste and sliding them forward, closing off the space behind so nothing can slip backward. This wave takes somewhere between 8 and 20 seconds to travel the full length of the esophagus, a leisurely pace considering that swallowing itself takes less than a second, and it is strong enough and coordinated enough that it will carry food downward regardless of the body's orientation in space. Gravity helps a little, particularly with liquids, which tend to arrive well ahead of the muscular wave and simply pool and wait. But solids depend almost entirely on peristalsis, which is why swallowing works whether you are sitting at a table or lying on your side in the dark, drifting towards sleep with the last few sips of water from a glass on the nightstand. At the very end of this muscular tube sits a ring of tissue called the lower esophageal sphincter, and understanding what a sphincter actually is will make a great deal of the rest of the digestive system easier to picture, because there are several more of them ahead. A sphincter is simply a ring of muscle that can tighten to close a passage or relax to open it, functioning something like a drawstring at the neck of a bag. Pull it snug and nothing gets through. Loosen it and the opening widens. The lower esophageal sphincter stays contracted, closed, most of the time, which is precisely what you want, because just on the other side of it sits a chamber full of acid strong enough to dissolve a great many things you would rather it didn't touch. When a wave of peristalsis approaches carrying food or drink, the sphincter relaxes just long enough to let the bolus pass through into the stomach below, and then closes again, usually within a few seconds, sealing the boundary once more. This arrangement generally works with a quiet reliability that most people never think about, which is exactly the sign of a well-functioning system. The ones you notice are the ones that are failing, but the seal is not always perfect. Certain things can cause that lower sphincter to relax at the wrong moment, or to relax too far, or simply to sit a little looser than it should. A very large meal that stretches and presses on the stomach from below, lying down too soon after eating. Certain foods, including chocolate, mint, and fatty dishes, along with caffeine, alcohol, and, notably, pregnancy, during which rising hormone levels can soften the muscle's tone considerably. When the seal loosens at an inopportune time, a small amount of stomach acid can travel backward up into the esophagus, producing the familiar burning sensation behind the breastbone that most people simply call heartburn, a slightly misleading name since the heart has nothing to do with it, but one that has stuck around since long before anyone understood the actual anatomy involved. The esophagus, unlike the stomach, has no thick protective mucus lining built to withstand acid, so even a small backward splash is enough to be felt quite distinctly, and if it happens often enough over months or years, it can gradually irritate the lining in ways that are worth taking seriously rather than simply enduring. For most people, though, it is an occasional, forgettable event, corrected within moments as the sphincter reasserts itself and a following swallow, even just of saliva, helps rinse the area clean. Past this sphincter, the bolus finally arrives in the stomach, and it is worth pausing here, because the stomach tends to be pictured as a simple holding tank, a sort of biological sac, when in fact it behaves more like a highly specialized workshop with distinct jobs happening in different regions. Shaped something like a curved pouch or, if you prefer a gentler comparison, like a comma tilted on its side, the stomach sits just beneath the ribs on the left, tucked under the diaphragm, and it can expand remarkably to accommodate a large meal, stretching from a resting volume of somewhere around 50 milliliters, not much more than a few tablespoons, up to well over a liter when generously filled, thanks to folds in its lining called rugae, which flatten out gradually as the stomach fills the way pleats in a skirt smooth out as it is stretched. The upper portion of the stomach tends to relax and expand to receive incoming food with relatively gentle activity, functioning largely as a reservoir, a holding area where food can arrive and settle without being immediately churned. But the lower two-thirds of the stomach is a different matter entirely, and this is where the real mechanical work happens. Here, 3 layers of muscle, running in 3 different directions, longitudinal, circular, and diagonal, an arrangement unique to the stomach among all the organs of the digestive tract, contract in coordinated waves, squeezing and folding the food with considerable force. This churning motion mixes the bolus thoroughly with gastric juice, breaking it down mechanically much the way a slow, powerful kneading motion works dough, folding it over itself again and again until what enters as recognizable chunks of food gradually becomes something else entirely, a thick, semi-liquid mixture the body calls chyme, gray-white and acidic, bearing very little resemblance to whatever meal it started as. And what, exactly, is chyme made of, once you strip away its appearance and look instead at the chemistry hidden inside it? This is worth sitting with for a moment. In the same unhurried way, the stomach itself takes its time, because nearly everything that will happen for the rest of digestion depends on the answer. A meal, whatever else it might be, a slice of bread, a piece of fish, a spoonful of rice, is, from the body's perspective, mostly a tangle of very large molecules, built by plants and animals for their own purposes, and none of those molecules were built with human absorption in mind. They are too big, too complicated, too oddly shaped to slip through the lining of the gut and into the bloodstream. So before any of it can nourish a single cell, it first has to be taken apart, patiently and specifically, into pieces small enough and simple enough to pass through. Consider carbohydrates first, since they tend to make up the largest share of most meals. A slice of bread, chemically speaking, is mostly starch, and starch is nothing more than glucose, a simple sugar, one of the smallest and most familiar molecules in biology, strung together in long repeating chains, sometimes thousands of units long. Picture a strand of pearls, each pearl identical, looped and coiled into a compact bundle, and you have something close to the shape of amylose, one of the two main forms of starch. The other, amylopectin, branches outward instead, more like a tree with countless small twigs than a single strand, which makes it bulkier and, as it turns out, a little slower to break apart. Digesting starch means snipping this long chain into shorter and shorter pieces, eventually down to individual glucose units, and this work actually begins surprisingly early, back in the mouth, where an enzyme in saliva called amylase starts nibbling at the chain the moment food is chewed. That process pauses once food reaches the stomach. The acid there is too hostile for salivary amylase to keep working, but it resumes again a little further along, once the meal reaches the small intestine, where a fresh supply of amylase arrives from the pancreas to finish the job, cutting the remaining chains down into pairs of linked sugars, which still need one more step, performed by enzymes stationed along the intestinal lining itself, before they become single, freestanding glucose molecules small enough to be absorbed. Proteins present a related but distinct kind of puzzle. Where starch is a simple repeating chain, a protein is more like a long, intricately folded ribbon, built not from one repeating unit, but from 20 different amino acids, strung together in a specific sequence, and then folded, twisted, coiled, tucked into itself, into a precise three-dimensional shape that determines what the protein can do. A strand of muscle fiber from a piece of meat, or the proteins bound up in a spoonful of beans, arrive in the stomach still holding much of that folded structure, and the first task is almost architectural rather than chemical. The acid in the stomach helps to unfold these proteins, loosening the folds, and turns the way steam loosens the wrinkles from fabric, exposing the chain so that enzymes can actually reach it. Pepsin, the main protein-digesting enzyme of the stomach, only works well in a strongly acidic environment, which is one of the reasons the stomach maintains such an aggressively low pH in the first place. A pH that would damage almost any other tissue in the body, but is, for pepsin, simply the right condition to do its work, cutting the unfolded protein chain into shorter fragments. Those fragments then travel onward to the small intestine, where pancreatic enzymes with names like trypsin and chymotrypsin continue the cutting. And finally, enzymes anchored to the intestinal lining trim what remains down into individual amino acids, or occasionally pairs and triplets of them, small enough at last to cross into the bloodstream. Fats ask for an entirely different approach because of a simple physical fact. Fat and water do not mix. A fat molecule, or triglyceride, consists of a small backbone called glycerol with 3 long fatty acid chains hanging off it, like 3 tails on a kite, and these tails are markedly unwilling to dissolve in the watery fluid that fills the digestive tract. Left alone, fat tends to clump into large, greasy globules, the way a spoonful of oil poured into a glass of water will bead up rather than dissolve, no matter how vigorously the glass is stirred. This is a genuine problem for digestion, because enzymes can only work on the surface of a fat globule, where they can actually make contact with it, and a single large globule has comparatively little surface area relative to its size. The solution arrives from the liver in the form of bile, a greenish-yellow fluid stored in the gallbladder and released into the small intestine at mealtimes specifically to deal with this problem. Bile doesn't break any chemical bonds itself. Instead, it acts something like dish soap breaking up grease in a sink. physically shattering large fat globules into a fine mist of much smaller droplets, dramatically increasing the total surface area exposed to the surrounding fluid. Only once fat has been divided this way can pancreatic lipase, the main fat-digesting enzyme, get enough purchase on it to clip the fatty acid tails away from the glycerol backbone, producing free fatty acids and partial glycerides small enough to be absorbed. Not everything in a meal needs this kind of dismantling, though. Vitamins and minerals, for instance, are already small, simple molecules or ions by the time they enter the body. A molecule of vitamin C or a single atom of iron doesn't need to be broken into pieces because it isn't built from repeating chains the way starch or protein is. What it needs instead is simply to be released from whatever food matrix has been holding it in place, and then carried across the intestinal lining, often with the help of specific transport proteins built for exactly that purpose. Iron, for example, requires the presence of a particular carrier to cross into the bloodstream in useful quantities. One reason iron deficiency has remained such a persistent and widespread problem throughout human history, long before anyone understood the chemistry behind it. Fat-soluble vitamins, meanwhile, A, D, E, and K, tend to travel along with dietary fat and rely on the same bile-assisted process to be absorbed, which is part of why a very low-fat meal can sometimes leave the body less able to make use of them. Water, for its part, isn't digested at all, in the sense of having any chemical bonds broken. It simply moves, passively, across the intestinal lining, following concentration gradients created by the absorption of everything else. Wherever sugars and salts are being pulled into the bloodstream, water tends to follow along quietly behind them, drawn by simple osmotic pressure rather than any enzyme's effort. And then there is fiber, which occupies a curious position in this whole story, because in a very real sense the human body cannot digest it at all. Plant fibers such as cellulose are, chemically, chains of glucose not unlike starch, but linked together with a slightly different kind of bond, one that human digestive enzymes simply are not built to cut. It is a small structural difference, almost trivial to describe, and yet it is enough to render an entire class of molecules essentially untouchable by anything the small intestine has to offer. Fiber, as a result, largely passes through this stretch of the gut unchanged, still bulky, still intact, carrying on toward the large intestine, where an entirely different community of residents, trillions of bacteria, patiently waiting further down the line, will take up the task that human enzymes were never equipped to finish. But before we follow that fiber down into the large intestine, a journey we'll take a little later, it's worth pausing here, in the upper part of the small intestine, because this is exactly the point where three of the body's quieter, less celebrated organs make their presence known. Everything we've discussed so far has depended on their contributions without our really stopping to meet them, so let's slow down and meet them properly: the liver, the gallbladder, and the pancreas. Start with the liver, if only because it's the largest of the three, and in many ways the most administratively complicated organ in the entire body. It sits tucked up under the ribs on the right side, a dark reddish-brown wedge weighing around 3 pounds in an adult, and it performs so many distinct chemical jobs, by some counts several hundred of them, that early anatomists struggled to settle on what it was even for. The ancient Greeks thought it might be the seat of the emotions, or even of the soul itself, which sounds strange until you consider how much it actually does behind the scenes to keep a body steady and functioning. It's not sensing joy or sorrow, but it is, in a very literal sense, constantly managing the internal chemistry that everything else depends on. One of its jobs, and the one most relevant to our story so far, is the production of bile. Bile is a yellowish-green fluid, thick and faintly bitter, made continuously by liver cells and then sent down a small duct toward the gallbladder for storage. It isn't an enzyme, it doesn't break any chemical bonds itself, but it performs a task that's arguably just as essential, which is emulsification. Picture a bowl of oil and vinegar left standing on a counter. Left alone, the oil gathers into globules and floats, refusing to mix, because fat and water simply don't want to associate with one another. Bile solves this problem the same way a drop of dish soap does when it's swirled into a greasy pan. It has one end that's attracted to fat and another end that's attracted to water, and so it wedges itself between the two, breaking large fat globules into thousands of much smaller droplets and holding them suspended in the watery environment of the intestine. This matters enormously, because the enzymes that actually digest fat can only work at the surface of a fat droplet. They can't reach inside a large, sealed clump. So, by multiplying the surface area available, bile turns what would be a slow, inefficient process into something the body can actually keep pace with. The gallbladder itself does not make bile. That credit belongs entirely to the liver, but it serves as a kind of storage tank, a small pear-shaped pouch tucked beneath the liver that concentrates and holds bile between meals, waiting. When a fatty meal arrives in the stomach and begins moving into the small intestine, hormonal signals travel back and cause the gallbladder to contract, squeezing its stored bile out through the bile duct and into the intestine at just the moment it's needed. It's a remarkably elegant piece of timing. The body doesn't waste bile trickling out constantly, but instead releases it in a coordinated burst tied to the actual arrival of fat. People who have had their gallbladder removed, a fairly common surgery, can still digest fat reasonably well afterward, because the liver keeps producing bile regardless and simply sends it along more continuously rather than in a stored burst. A good illustration of how the body often has backup arrangements for even its more specialized systems. Just as this fatty, bile-treated material moves along, something else has to happen, because the fluid arriving from the stomach is intensely acidic, a legacy of all that hydrochloric acid we discussed earlier, still clinging to the food as it passes through the sphincter into the small intestine. If left unaddressed, that acidity would damage the delicate lining of the intestine, which, unlike the stomach, has no thick mucus armor to protect it. This is where the pancreas enters the story, tucked in behind the stomach, an elongated gland that looks a little like a flattened pear or a stretched-out fish, and it responds to the arrival of acidic material by releasing bicarbonate, the same alkaline compound found in ordinary baking soda, directly into the small intestine. The bicarbonate neutralizes the acid almost immediately, the way pouring baking soda over a vinegar spill causes a fizzing reaction that settles into something mild and harmless. Within moments, the environment inside the intestine shifts from something acidic enough to dissolve metal to something closer to neutral, gentle enough for the next stage of digestion to proceed safely. And it's in that same gentle, neutralized environment that the pancreas delivers its second great contribution, enzymes, an entire cocktail of them, each built to handle a different kind of molecule. There are enzymes for carbohydrates, continuing the work that saliva began back in the mouth. There are enzymes for proteins, picking up where the stomach's pepsin left off, cutting long protein chains down into smaller and smaller fragments. And there are enzymes for fats, the ones that finally get to do their real work once bile has broken those fat globules into small enough droplets for the enzymes to reach. It's worth pausing on how remarkable it is that the pancreas manufactures enzymes capable of dissolving protein and fat, given that the pancreas itself is made of protein and fat, a kind of built-in hazard that the organ manages by keeping these enzymes inactive until they've actually left the gland and arrived safely in the intestine, where they're switched on by other enzymes waiting there. It's a bit like shipping a container of reactive chemicals, with the activating agent kept in a separate compartment until the moment of use. A safeguard against the pancreas essentially digesting itself, which, when this system fails, is exactly the kind of medical emergency it can lead to. But the pancreas has another life entirely, one that has nothing to do with the intestine at all. And this is where things get interesting. Scattered throughout the pancreatic tissue, in small clusters that make up only about 2% of the organ's mass, are cells that don't send anything into the gut. Instead, they release their products directly into the bloodstream, insulin and glucagon among them, hormones responsible for managing blood sugar levels throughout the entire body. When sugar levels rise after a meal, insulin is released to help usher glucose out of the blood and into cells for use or storage. When levels fall between meals, glucagon nudges stored sugar back out of the liver and into circulation. It's a strange kind of organizational overlap, really. One gland doing double duty as both a digestive contributor and an endocrine regulator, its two roles operating almost independently of one another within the same small structure. And this brings us back, in a way, to the liver, because the liver is deeply involved in that blood sugar story too. Once nutrients have been absorbed from the small intestine, the very first place much of that nutrient-rich blood travels is not the heart, not the rest of the body, but the liver, routed there directly through a special vessel called the portal vein, almost as if the body insists on giving the liver first inspection rights over everything that has just been absorbed. The liver takes in that glucose-heavy blood and decides, moment to moment, how much sugar the rest of the body actually needs right now, storing the surplus as a compact molecule called glycogen, releasing it back out later when blood sugar starts to dip. It performs a similar sorting function for nutrients of every kind, not just sugar, deciding what to send onward, what to store, and notably, what to break down and neutralize before it ever reaches the rest of the body at all. A filtering role that becomes especially important once we start considering the things a person eats or drinks that the body would honestly be better off without. Before any of that sorting can happen, though, before the liver gets its first look at anything, the nutrients have to actually leave the gut and enter the bloodstream in the first place. And that happens back in the small intestine, in a process so quietly remarkable that it's easy to walk right past it without appreciating what's going on beneath the surface, literally beneath the surface, because the surface itself is the whole trick. If you were to lay the small intestine out flat, stretch it end to end, and smooth it like a bedsheet, it would run somewhere around 20 feet in an adult, sometimes a bit more, sometimes a bit less, coiled up inside the abdomen, in loops that somehow never seem to tangle, no matter how much the body shifts and moves throughout a day. 20 feet is already a fair bit of internal plumbing, but length alone wouldn't be nearly enough to do the job the small intestine needs to do, which is to pull nearly every useful nutrient out of the liquefied meal passing through it before that meal moves on and is lost for good. A smooth tube, 20 feet long, no matter how long you let it work, simply wouldn't have enough surface area in contact with the food to absorb everything efficiently. So the body does something clever. It doesn't just lengthen the tube. It folds it, and then folds the folds, and then folds those. The first layer of folding is visible without any special magnification. Deep, circular ridges called plicae circulares, folds of the intestinal wall itself that spiral gently around the inner tube, like the ridges on the inside of a seashell, or like the accordion folds of a paper fan, forcing the contents of the intestine to swirl and tumble as they pass, rather than sliding straight through in a lazy, uneventful line. These folds alone increase the surface area by a meaningful amount, maybe threefold over a plain tube, but that's only the beginning. Growing out of those folds, covering every inch of them, are millions of tiny finger-like projections called villi, each one so small it's only barely visible to the naked eye, appearing to the unaided eye more like the texture of velvet than like individual structures. Under a microscope, though, a patch of intestinal lining looks almost like a dense shag carpet, or perhaps more accurately, like a forest of tiny fingers, all reaching upward into the passing stream of digested food, swaying gently, each one working independently to pull in whatever nutrients happen to brush against it. There are perhaps 10 to 40 villi packed into a single square millimeter of tissue, an almost absurd density when you stop to picture it, and each of those millions of villi multiplies the absorptive surface again by another order of magnitude. And then, just when it seems the body must have run out of tricks, there's one more layer of folding, this one too small to see even under an ordinary microscope. Each individual cell on the surface of each individual villus is itself covered in thousands of even tinier projections called microvilli, so fine and so densely packed together that under strong enough magnification they resemble the bristles of a very fine brush, which is in fact exactly what this layer is called, the brush border. If a single villus is like a finger reaching into the intestinal contents, then the microvilli are like the ridges of a fingerprint on that finger, a texture layered onto a texture, layered onto a texture. Folds within folds within folds, each level far too small to notice on its own, and yet together they transform what could have been a smooth 20-foot tube into something with an absorptive surface that some researchers have compared, loosely, to the size of a tennis court, an estimate that has been debated and revised over the years, with some more careful modern measurements suggesting something closer to the size of a small studio apartment rather than a full court. Even the more conservative figures are still remarkable. All of that surface, somehow, folded and packed and coiled into a space not much larger than what could fit comfortably inside your own abdomen. Why go to such extraordinary lengths for surface area? Because absorption, at its core, is a matter of contact. A nutrient molecule can only cross into the body if it happens to touch a cell capable of taking it in. And the more surface there is for that contact to occur, the faster and more completely the job gets done. It's not unlike drying laundry. A shirt bunched into a tight, wet ball will take a long time to dry because so little of its surface is exposed to the air. Spread that same shirt out flat, and it dries far more quickly, simply because more of its fabric is in contact with the surrounding air at once. The small intestine, in its own quiet way, has arranged itself to be maximally unbunched, maximally exposed, every fold and villus and microvillus existing purely to put as much living tissue as possible in direct contact with the nutrients passing by. But contact alone isn't quite the whole story either, because not every molecule can simply wander across a cell membrane on its own. Cell membranes are, by design, somewhat selective barriers, made largely of fatty material that water-soluble substances don't cross easily without help. So embedded in the membrane of every one of those microvilli are specialized transport proteins, each one shaped to recognize and usher across a particular kind of molecule. Picture a series of small, precisely shaped doorways built into a wall, each doorway sized and shaped for one specific kind of guest. One type of transport protein exists mainly to pull glucose in, often working in a clever partnership with sodium, the two moving across the membrane together, the flow of sodium down its own concentration gradient, essentially dragging glucose along with it, almost like a person holding a door open just long enough for someone else to slip through behind them. Other transport proteins are shaped for individual amino acids, or for pairs of amino acids linked together, or for the breakdown products of nucleic acids. Each one is a small, dedicated worker, tuned by evolution over an immense stretch of time to recognize its particular passenger and let almost nothing else through. Once a nutrient has been ushered into one of these absorptive cells, though, its journey still isn't over, because it now has to make its way into the body's actual transport systems, the rivers that will carry it onward to where it's needed. And here the story splits into two rather different paths, depending on what kind of nutrient is involved. Sugars and amino acids, being reasonably comfortable dissolving in water, pass out through the far side of the absorptive cell and into a network of small capillaries running through the core of each villus, tiny blood vessels so narrow that red blood cells sometimes have to pass through them single file. From there, that nutrient-laden blood collects into larger and larger vessels, eventually converging into that portal vein that carries everything straight to the liver for inspection, exactly the route the liver seems to insist upon. Fats, though, take a different road entirely, because fat and water don't mix, and a fatty molecule dropped directly into a watery bloodstream would behave badly, clumping together in ways that could clog the very vessels meant to carry it. So instead, absorbed fats are packaged inside the intestinal cells into small, spherical particles, wrapped in a thin shell that allows them to move safely through a watery environment, and these particles are released not into the blood capillaries at all, but into a different kind of vessel running through the core of each villus, a delicate, blind-ended channel called a lacteal, part of the body's lymphatic system rather than its bloodstream. The lacteals gather up the fat, carry it onward through a network of lymphatic vessels, and eventually deliver it into a large vein near the neck, allowing it to join general circulation only after bypassing the liver's usual first inspection, a quiet exception to the rule, one that will matter quite a bit once we start thinking more closely about what happens to the fat a person eats, and where, exactly, it goes from there. For now, though, let's follow that portal blood, the stream carrying the sugars and amino acids, because its next stop is unavoidable and rather important. Every drop of blood leaving the small intestine, laden with the fruits of digestion, has to pass through the liver before it's allowed to mingle with the rest of the body's circulation. This is not a small organ to pass through casually. The liver is the largest solid organ inside a person, tucked up under the right side of the rib cage, weighing something in the neighborhood of 3 pounds in an adult, dense with blood and busy with more distinct chemical tasks than perhaps any other tissue in the body. And it receives this portal blood not as an afterthought but as its primary supply, its main reason for being positioned exactly where it is. Roughly 3/4 of the blood flowing into the liver arrives this way, straight from the gut, still carrying the chemical signature of whatever was just eaten. Picture, for a moment, what the liver actually encounters in this blood. There's glucose, freshly absorbed, its concentration having just risen after a meal, in a way the body cannot simply ignore. There are amino acids, 20 different kinds, each with its own shape and its own eventual purpose. There may be alcohol, if that's what was in the glass beside dinner. There may be a medication, dissolved and absorbed alongside the food it was taken with. And there may be less welcome hitchhikers, too. Chemical byproducts of digestion, or occasionally something actively harmful. The liver's task with all of this is not passive filtration, the way a coffee filter simply catches grounds while letting liquid through. It's closer to a customs inspector working at enormous speed, examining nearly everything that passes, deciding what to let through unchanged, what to modify, what to store for later, and what to break down and neutralize before it ever reaches the heart, the brain, or anywhere else that might be more sensitive to it. Take glucose as the clearest example, since it illustrates the liver's whole philosophy rather nicely. After a meal, blood glucose rises, and a rise in blood glucose is, from the body's perspective, both an opportunity and a small hazard. An opportunity, because glucose is fuel, the preferred energy source for many cells and very nearly the only fuel the brain can use under normal circumstances. A hazard, because if blood glucose is allowed to climb too high and stay there, it starts to do quiet damage to blood vessels and tissues over time, the kind of damage that unfolds across years rather than minutes, but damage nonetheless. So the liver, sensing this rise, along with a hormonal signal called insulin released by the pancreas in response to that same rise, begins pulling glucose out of the bloodstream and storing it. It does this by linking individual glucose molecules together into a long, branching chain called glycogen, a storage molecule that can be built up during and after a meal, and then broken back down, glucose released 1 unit at a time, during the hours between meals or overnight, whenever blood sugar starts to dip, and the body needs a steady supply, without having to wake someone up to go eat something. The liver can hold perhaps 100 grams or so of glycogen this way, along with a somewhat larger reserve stored in muscle tissue, though muscle glycogen is kept for the muscle's own private use, rather than shared out to the rest of the body. This is, in a sense, the liver keeping the household books balanced. Too much glucose arriving at once, and it gets tucked away into savings. Too little available between meals, and savings get drawn down to cover the gap. It's a remarkably smooth system, one that, in a healthy person, keeps blood glucose hovering within a fairly narrow range almost all the time, even though the actual input, what a person eats and when, is wildly irregular. Nobody eats in a perfectly steady drip. Meals come in bursts, sometimes large, sometimes skipped altogether, and yet blood sugar mostly doesn't swing wildly to match, because there's this quiet buffering system working underneath, hour after hour, mostly without anyone thinking about it at all. Amino acids get a somewhat different treatment. The liver does take some of them, using them to build its own proteins, or to manufacture the various plasma proteins that circulate in blood, things like albumin, which helps keep fluid properly distributed between blood vessels and surrounding tissue, or the clotting factors that allow a cut to eventually stop bleeding. But most amino acids are allowed to pass on through, out into general circulation, because the body's tissues everywhere are in a more or less constant state of needing them. Every cell contains proteins that wear out and need replacing, enzymes that get used up and rebuilt, structural elements that fray with ordinary use the way any working machine does. A skin cell needs amino acids to patch up its structural proteins. A muscle fiber, especially after being used more than usual, needs amino acids to repair small tears in its contractile filaments, the process that, incidentally, is part of what makes muscles grow stronger after exercise rather than simply going back to exactly how they were before. Even hair and nails, which might seem like inert material, are built continuously from protein, cell by cell, at their hidden growing edges. Once glucose and amino acids leave the liver's immediate oversight and travel onward through the bloodstream, they eventually arrive at the smaller vessels feeding into individual tissues, and there they cross out of the blood entirely and into individual cells, which is really where the story of a meal finally reaches its destination. A cell is, among other things, a very small and very busy chemical factory, and glucose entering it doesn't just sit around. It's drawn into a sequence of reactions, occurring first in the fluid interior of the cell and then inside small bean-shaped structures called mitochondria, sometimes described, perhaps a little too simply but not inaccurately, as the cell's power plants. Through this sequence, the chemical energy locked inside a glucose molecule's bonds gets gradually released and captured, not in one violent burst, but in small, controlled steps, and stored in a molecule called ATP, adenosine triphosphate, which functions as a kind of universal energy currency inside cells. Nearly everything a cell does, moving, dividing, building new proteins, pumping ions across membranes to maintain the right internal chemistry, draws on this ATP supply, spending it and needing it replenished continuously, thousands of times over, every single day, in every one of the trillions of cells that make up a person. Amino acids, meanwhile, once they've reached a cell that needs them, get assembled into new proteins according to instructions read out from that cell's own genetic material. Each protein folding into a specific three-dimensional shape suited to a specific job, whether that's an enzyme speeding along some chemical reaction, a structural fiber holding a tissue's shape, or a signaling molecule carrying a message from one part of the body to another. And here is something worth sitting with for a moment. In the quiet way that bodies tend to keep their most remarkable feats hidden from ordinary attention, the amino acid that arrived at the dinner table as part of a piece of fish or a spoonful of lentils might, within hours, become part of the actual physical structure of a person's own body, woven into a muscle fiber or folded into an enzyme working somewhere deep inside a cell, indistinguishable, once it's there, from any other atom that happens to make up that particular person. There is no permanent stamp on a molecule marking where it came from. Matter simply gets reused, absorbed into new arrangements, and this is happening constantly, at every moment, whether anyone happens to be paying attention to it or not. But not every meal's worth of glucose and amino acids gets used immediately, and the body has quiet contingency plans for the surplus as well. Plans that lead somewhere rather different from the glycogen stores in the liver and muscle, and that bring fat, still making its own separate way through the lymphatic system, back into the larger picture of how a body decides what to keep and what to spend. By the time this conversation about fat and its separate route through the lymphatic system settles, the material that started the whole journey as a mouthful of food has largely finished being useful in the way most people imagine digestion working. That is, broken down and absorbed and carried off into cells. What's left, moving along through many feet of small intestine, has already surrendered its glucose, its amino acids, most of its fat, a good portion of its vitamins and minerals. And yet it is not nothing. It is not waste in any simple sense, not yet. It is, instead, arriving at the entrance to a different kind of organ altogether, one that works on entirely different principles, at an entirely different pace, and that has its own quiet agenda running alongside whatever a person happens to be doing with the rest of their day. This is the large intestine, sometimes called the colon, and it begins where the small intestine ends, down in the lower right part of the abdomen, at a valve that controls what passes through, and, just as importantly, what doesn't come back the wrong way. The material entering here is watery, loose, still carrying a great deal of liquid, along with fiber that resisted digestion in the small intestine, some unabsorbed nutrients, sloughed off cells from the lining of the gut, and vast, almost unimaginable numbers of bacteria. If the small intestine is where the body does its careful, targeted extraction of energy and building blocks, the large intestine is where something slower and, in its own way, stranger takes over. The first job of the large intestine is water recovery, and this alone is worth pausing on, because the numbers involved are larger than most people would guess. Across a single day, a person's digestive system handles many liters of fluid, not just from drinking, but from saliva, from stomach secretions, from the pancreas and the liver and the intestinal lining itself, all of it pouring into the gut to help break food down and keep everything moving smoothly. Almost all of that fluid gets reclaimed before it's lost. The small intestine recovers a great deal of it, but the large intestine finishes the job, pulling water back through its lining and into the bloodstream so efficiently that what began as a loose, almost soup-like slurry entering from the small intestine is gradually transformed, over the many hours it spends traveling the length of the colon, into something firmer, more solid, more recognizable as stool. Without this recovery, a person would lose an enormous volume of water every single day, and dehydration would follow quickly. This is part of why conditions that interfere with the large intestine's ability to absorb water, certain infections, certain inflammatory states, can be so serious, because the body suddenly finds itself losing fluid it was counting on getting back. The lining of the large intestine looks different from the lining of the small intestine in ways that reflect this different job. There are no villi here, none of those small finger-like projections that gave the small intestine such enormous surface area for absorbing nutrients. The large intestine doesn't need that kind of surface area for absorbing glucose or amino acids, because by the time material reaches it, those nutrients are largely gone already. Instead, the lining is smoother, organized into simple pits and glands, and it's rich in cells that produce mucus, an almost startling amount of mucus, continuously. That mucus matters more than its unglamorous reputation might suggest. It coats the inside of the colon, protecting the delicate lining from the friction of increasingly solid, increasingly concentrated material moving past, and it also acts as a kind of lubricant, letting that material glide along rather than scraping or catching. Beyond the purely mechanical role, mucus forms a barrier between the trillions of bacteria living in the colon and the tissue of the gut wall itself, a barrier that keeps those bacteria at arm's length, so to speak, allowing a kind of peaceful coexistence rather than an ongoing conflict. When that mucus layer gets thinner than it should be, for reasons researchers are still working to fully understand, bacteria can end up closer to the intestinal wall than is comfortable for the immune system, and inflammation can follow. So this unglamorous, easily overlooked substance is, in its quiet way, doing something close to peacekeeping. Movement through the large intestine looks nothing like movement through the small intestine. Where the small intestine relies on those relatively brisk waves of peristalsis, carrying material through in a matter of hours, the large intestine is unhurried by comparison. Material can spend anywhere from about 12 hours to several days making its way through, depending on the person, their diet, their hydration, their activity level, even their stress and sleep. Much of the movement within the colon is a slow, segmenting kind of motion, gentle contractions that mix material back and forth in place rather than propelling it forward with any real urgency, giving the bacteria living there and the lining itself plenty of time to do their work of absorption and fermentation. Every so often, though, usually a few times a day, and often after a meal, something called a mass movement occurs, a stronger, more coordinated contraction that sweeps a larger volume of material a significant distance forward, sometimes all the way toward the rectum. This is part of why people often feel the urge to have a bowel movement shortly after eating, particularly after breakfast, because the simple presence of new food entering the stomach can trigger this reflex further down the line, an old and reliable pattern of the nervous system tying one end of the digestive process to the other. Fiber plays an outsized role in all of this, and it's worth being specific about what fiber actually is, because the word gets used rather loosely. Fiber refers to certain carbohydrates and related plant compounds that human digestive enzymes simply cannot break down, not because of any flaw in the system, but because the body never evolved the right enzymes for the job. Some fiber is soluble, meaning it dissolves in water and tends to form a gel-like substance as it travels through the gut, and this kind is found in foods like oats, beans, apples, and citrus fruit. Other fiber is insoluble, meaning it doesn't dissolve, and instead adds bulk and structure to what moves through the colon, found in things like wheat bran, many vegetables, and the skins of various fruits. Both kinds change the character of the stool, though in somewhat different ways. Insoluble fiber tends to speed transit along and adds firmness and bulk, which is part of why diets low in fiber are so often associated with harder, more difficult to pass stool, and why increasing fiber intake is such a common recommendation for that particular kind of discomfort. Soluble fiber, meanwhile, tends to soften stool and slow transit slightly, which sounds contradictory until you consider that the effects of fiber aren't really about speeding things up or slowing things down in some simple, single direction, but about restoring a kind of steady, well-regulated rhythm, whatever a particular body happens to need at a particular time. But fiber does something else as well, something that has become a much larger part of the scientific conversation in recent decades, and that is feeding the bacteria living in the colon. Because human enzymes cannot break fiber down, that job falls instead to the bacteria themselves, an enormous and varied community, numbering in the trillions, made up of hundreds of different species, each with its own preferences for what it can and cannot ferment. When these bacteria break fiber down through fermentation, they produce a range of byproducts, among them short-chain fatty acids, compounds that turn out to matter a great deal, both to the health of the colon's own lining, which uses some of these fatty acids directly as fuel, and, according to a growing body of research, to processes elsewhere in the body as well, including aspects of immune function and metabolism. Different types of fiber feed different populations of bacteria, which is part of why a varied diet, rich in many different plant foods rather than just one or two, tends to support a more varied community of microbes in the colon, and why researchers increasingly think about fiber not simply as roughage that keeps things moving, but as something closer to a food source for an entire ecosystem living quietly inside a person, one whose composition and behavior scientists are still, even now, only beginning to map. It's worth sitting with what fermentation actually is, in a literal sense, because the word tends to call up images of bread rising or wine aging in a cellar, and those images aren't wrong, exactly. They're just happening in a different location than most people imagine. Fermentation, at its core, is simply what happens when microorganisms break down a food source in the absence of oxygen, extracting the energy they need to live and multiply, and releasing various compounds as a result. The colon, dim and warm and largely oxygen-free, turns out to be an excellent setting for this kind of activity, not unlike the sealed crock a home fermenter might use to make sauerkraut or kimchi, except that the crock in this case is several feet of muscular tube, and the vegetables fermenting inside it are whatever fibrous plant material survived the trip through the stomach and small intestine without being broken down. The bacteria doing the fermenting were there already, waiting, part of a community that took up residence in a person's gut sometime in early life and has been shifting and adjusting ever since, responding to every meal, every illness, every course of antibiotics, every stretch of stress or good sleep or poor sleep, in ways that scientists are still working to fully understand. The scale of this community is worth pausing on, if only because it's easy to state a number like trillions of bacteria and have it slide past without really landing. A commonly cited estimate puts the number of microbial cells in a person's gut at somewhere in the same order of magnitude as the number of human cells in their entire body, though the precise ratio has been revised several times as measurement techniques have improved, and researchers now tend to be more cautious about offering an exact figure. What's less disputed is the sheer diversity involved. Hundreds of different bacterial species in a typical gut, along with smaller numbers of other microorganisms, archaea and fungi, and viruses that infect the bacteria themselves, all coexisting in a kind of crowded, jostling neighborhood. Some of these species are found in nearly everyone, forming something like a common core. Others vary enormously from one person to the next, shaped by diet, geography, birth method, whether someone grew up with pets or siblings or on a farm, and factors researchers haven't fully identified yet. Two healthy adults, eating similar diets and living in the same city, might still carry gut communities that look strikingly different under a microscope, and both, as far as anyone can tell, might be perfectly fine. Within this crowded neighborhood, competition is a constant, quiet feature of daily life. Bacteria are not particularly interested in cooperating with each other in any sentimental sense, whatever the word community might suggest. They are interested, insofar as a bacterium can be said to be interested in anything, in acquiring the resources they need and reproducing before their neighbors do. This turns out to be useful to the person hosting them, because a densely packed, well-established community of familiar bacteria leaves very little room and very few unclaimed resources for a new arrival to exploit. A stray pathogen that manages to survive the acid of the stomach and reach the colon often finds every promising niche already occupied, every available nutrient already being consumed by bacteria that have had years, sometimes decades, to settle in and defend their territory. This phenomenon, sometimes called colonization resistance, is one of the clearer examples of how the resident microbial community can function as a kind of standing defense, not through anything as dramatic as an immune response, but simply through crowding, through the mundane fact of a space being full. It's part of why events that dramatically thin out this population, a severe course of broad-spectrum antibiotics being the most common example, can leave a person more vulnerable, for a while, to infections that a fuller, more established community might otherwise have crowded out. The short-chain fatty acids produced during fermentation deserve a slightly closer look, since they've become one of the more carefully studied outputs of this whole fermentation process. The three that come up most often in the research are acetate, propionate, and butyrate, each produced in different amounts depending on which bacteria are doing the fermenting and which fibers they're fermenting. Butyrate, in particular, seems to matter a great deal to the cells that line the colon itself, which use it as their preferred fuel source, more so than glucose, which is a little unusual since most cells in the body run primarily on sugar. A well-fed, well-functioning lining of the colon, nourished by a steady supply of butyrate, appears to maintain itself more effectively, repairing and replacing its cells at a healthy pace, and some researchers suspect that a poorly fed colon lining, one starved of butyrate because the diet feeding it lacks sufficient fiber, may be part of the picture in certain kinds of chronic gut inflammation, though the full relationship, including how much of it is cause and how much is consequence, remains an active area of study rather than a settled matter. Acetate and propionate travel further, some of it reaching the bloodstream, where researchers have found associations with processes like appetite regulation and how the body handles blood sugar, associations that are genuinely interesting and worth taking seriously, while also being the kind of finding that tends to get overstated in the retelling, turned into tidier, more definitive claims than the original research actually supports. Beyond fuel and beyond competition, there is a third role that has drawn increasing attention, which is communication, specifically between the resident bacteria and the immune system. It might seem strange, at first, that the immune system, whose job is broadly to distinguish self from foreign and to attack the foreign, would tolerate trillions of foreign organisms living in close contact with the intestinal lining, rather than mounting a constant, exhausting assault against them. But the relationship, as far as researchers can tell, is less like tolerance in the passive sense, and more like an ongoing negotiation, conducted over the entire span of a person's life. A substantial portion of the body's immune tissue is actually clustered around the gut, positioned there specifically because so much of the immune system's education, particularly in early childhood, happens through exposure to the bacteria living in that environment. Short-chain fatty acids appear to play a role in this negotiation as well, with some research suggesting that butyrate in particular can help promote the development of certain regulatory immune cells, cells whose job is essentially to calm the immune response down, to help it distinguish between an actual threat and the ordinary harmless presence of a bacterium that has lived peacefully in the colon for years. This is part of why some researchers have proposed connections between disruptions in the gut microbiome, early in life especially, and later development of allergic or autoimmune conditions, though it's worth being honest that this remains a hypothesis under active investigation, supported by real and interesting evidence, but not yet the kind of settled, fully mapped causal chain that would let anyone say with confidence exactly how much of any individual case of allergy or autoimmune disease traces back to events in the gut during infancy. It's this last point, really, that deserves the most emphasis, because the gut microbiome has, in the last 15 or 20 years, become one of the more heavily marketed areas of health science, with claims made about it that outpace what the underlying research actually demonstrates. The honest state of the field is one of genuine excitement paired with genuine uncertainty. Researchers can measure, with real precision now, which bacterial species are present in a given sample, and they can measure, with somewhat less precision, which short-chain fatty acids and other compounds those bacteria are producing. What remains much harder to establish, in most cases, is the direction of cause and effect, whether a particular pattern of gut bacteria is contributing to a health outcome or is simply a byproduct of it, shaped by the same diet or the same underlying condition that's producing the outcome independently. Add to this the fact that gut microbiomes vary so much between individuals that a pattern found in one study population doesn't always hold in another, and it becomes clear why so much of the field, for all its genuine promise, is still working out which findings will hold up and which won't, none of which makes the fermentation happening quietly in the colon any less real or any less worth understanding, even in outline, as one more example of how much of digestion depends not just on the body's own tissues, but on this second, invisible population living alongside them, whose full relationship with the rest of the body is still, even now, being written down for the first time. Let's step back from that invisible population for a moment and turn to a question that feels far more familiar, because almost everyone has asked it of themselves at some point during an ordinary day. Why, exactly, do we feel hungry? And why, 20 minutes into a meal, does that hunger seem to simply vanish, replaced by a sense of having had enough, sometimes even before the stomach itself feels physically full? The answer turns out to be one of the more elegant examples in the whole body of how a feeling that seems purely psychological, a mood, an urge, a craving, is in fact being generated by an intricate exchange of chemical messages between the gut and the brain, messages that are being sent and received continuously, whether or not a person is paying any attention to them at all. The story usually begins with an empty stomach, because it's the stomach, more than any other organ, that seems to sound the first alarm. When the stomach has been empty for a few hours, cells in its lining begin releasing a hormone called ghrelin, sometimes described, a little playfully, as the hunger hormone, and it circulates through the bloodstream until it reaches the brain, where it acts on a region called the hypothalamus, a small structure buried deep in the base of the brain that serves as something like a control room for basic bodily needs, hunger and thirst and temperature and sleep, all being coordinated, at least in part, from this same small cluster of tissue. Ghrelin levels rise before meals and fall after them, tracking hunger with a rhythm that's surprisingly regular, so regular that some researchers have suggested the body has learned, through habit, to anticipate meals at the times a person usually eats them, releasing ghrelin not just because the stomach is empty, but because the clock, in some sense, says it's time. Fullness works through a different set of signals, and it works more slowly than most people expect, which is one reason it's so easy to eat past the point of genuine satisfaction. As food enters the small intestine, cells there release a hormone called cholecystokinin, the same hormone mentioned earlier for its role in triggering the gallbladder to release bile, and it turns out this hormone does double duty, also signaling to the brain that food has arrived and that the pace of eating might reasonably slow. Later, as digestion continues, another hormone called GLP-1 joins the conversation, released from cells further down the intestine, reinforcing the message that enough has been eaten and further reinforcing, along the way, the release of insulin to help manage the sugars now entering the bloodstream. And there's leptin, a hormone released not by the gut at all but by fat tissue itself, providing the brain with a kind of long-term report on the body's energy reserves, a slower, quieter signal layered on top of the meal-to-meal fluctuations of ghrelin and cholecystokinin. It's the interaction of all these hormones together, arriving in the brain at different speeds and from different sources, that produces the felt experience of hunger and fullness, an experience that seems so simple from the inside and turns out, on closer inspection, to be the product of a small chemical committee. None of this chemical signaling would matter much, though, without a nervous system capable of receiving it and acting on it, and here, the digestive tract holds a secret that surprises most people the first time they hear it. Woven through the walls of the esophagus, the stomach, and the intestines is a network of neurons so extensive, so capable of independent action, that it's sometimes called the second brain, a phrase that sounds like exaggeration, but is not entirely undeserved. This network is known formally as the enteric nervous system, and it contains something on the order of 500 million neurons, a number that sounds small next to the roughly 86 billion neurons in the brain itself, but which is nonetheless larger than the neuron count of the spinal cord, and more than enough to run a remarkably sophisticated operation entirely on its own. The enteric nervous system can coordinate the rhythmic muscle contractions of peristalsis, adjust the release of digestive enzymes, and respond to the presence or absence of food, all without any instruction from the brain at all. This is easy to demonstrate, in fact, because sections of intestine removed from the body and kept alive in a laboratory dish will continue producing those same coordinated contractions, a small, isolated proof that the gut's nervous system is not merely a relay station for commands sent down from the head, but a genuine, semi-autonomous nervous system in its own right, doing much of its most important work in the dark, without supervision. That said, the gut and the brain are not really separate kingdoms, however independent the gut's local operations might be, and the primary line of communication between them is a single, remarkable nerve called the vagus nerve. The word vagus comes from the Latin for wandering, a fitting name, because this nerve doesn't take the shortest route to any single organ, but instead winds its way down from the brainstem through the neck and chest, branching out to touch the heart, the lungs, and nearly every organ of the digestive tract along the way, from the esophagus, down through the stomach, and much of the intestine. What's striking about the vagus nerve, and what surprised researchers when they first measured it carefully, is that the great majority of its fibers, something like 80 or 90%, carry information in the opposite direction from what most people would assume, not from the brain down to the gut, but from the gut up to the brain. The gut, in other words, is talking to the brain far more than the brain is talking to it, sending constant reports about stretch, about chemical composition, about the presence of certain bacterial byproducts, and the brain is doing a great deal of listening, weaving these reports, mostly below the level of conscious awareness, into mood, into appetite, into the vague, hard-to-name sense of well-being or unease that seems to rise up from somewhere in the middle of the body, rather than from any clearly locatable source. This helps explain something that almost everyone has experienced, but rarely stops to think about carefully, which is how directly emotional states seem to register in the stomach and intestines. A knot of anxiety before a difficult conversation, a stomach that seems to drop during a moment of fear, a loss of appetite during grief. These are not simply figures of speech, but reasonably accurate descriptions of what is happening physiologically, because the same nervous system that manages digestion is deeply entangled with the nervous system that manages stress. When the body perceives a threat, real or imagined, it shifts into a state sometimes called fight or flight, releasing stress hormones and redirecting the nervous system's attention toward the muscles and the heart, away from digestion, which in an emergency is, after all, a lower priority than escaping danger. Blood flow to the gut decreases, the normal rhythm of peristalsis is disrupted, and digestive secretions change, which is part of why chronic stress is so reliably associated with digestive complaints, from a churning stomach to changes in bowel habits that seem to have no other explanation. The gut, sensitive as it is to the body's chemical and mechanical state, turns out to be just as sensitive to the mind's emotional state, because as far as the nervous system is concerned, the two were never really separate categories to begin with. Nausea belongs to this same story, and it's worth pausing on because it's such a peculiar sensation, one that seems to come from nowhere and yet feels unmistakably specific. Nausea is generated by a region of the brainstem, informed by signals arriving from the vagus nerve, from the inner ear, and from a specialized area of the brain equipped to detect certain toxins directly in the bloodstream, all of it converging on a single protective purpose, which is to discourage the body from eating anything further, and, if necessary, to trigger vomiting as a way of expelling something that might be harmful. Motion sickness is one of the more interesting variations on this theme, arising when the inner ear, which senses motion and balance, reports one story to the brain, while the eyes, fixed on a stable object like the interior of a car or a book held steady on a lap, report a contradictory story of stillness. Some researchers believe the brain, faced with this mismatch, falls back on an old evolutionary assumption that such confusing sensory input is a sign of poisoning, since certain toxins are known to disrupt the inner ear's sense of balance, and so it responds in the way it would respond to any other suspected poison, with nausea and sometimes with vomiting, an overly cautious but not entirely unreasonable interpretation of a situation the body has never actually encountered, in the form of a moving vehicle. Gas, in this same spirit, is rarely a sign that anything has gone wrong. It's mostly just the ordinary byproduct of a body doing what it evolved to do, which is to let trillions of bacteria in the large intestine ferment the fibers and starches that the small intestine couldn't fully break down on its own. As these microbes feast on what's left of a meal, they release gases as a natural consequence of their metabolism: hydrogen, carbon dioxide, and in some people, methane, depending on which particular communities of bacteria happen to be thriving in their gut that week. Some of this gas is absorbed through the intestinal wall and breathed out through the lungs, which is part of why a person's breath can, in subtle ways, carry chemical traces of what's happening deep in their digestive tract. The rest moves onward and is eventually released, and the amount varies enormously from person to person, shaped by diet, by the particular mix of resident bacteria, and by how quickly food moves through the system. A food that produces almost no gas in one person might produce a great deal in another, not because one gut is healthier than the other, but because the bacterial populations are simply different, tuned by years of diet and circumstance to prefer different fuels. Bloating is a related but distinct experience, and it's one of the more curious puzzles in digestive physiology, because the feeling of fullness and tightness doesn't always correspond to an actual measurable increase in gas volume. Sometimes bloating does come from a temporary buildup of gas, perhaps because a meal was unusually rich in fermentable fibers, or because the muscles of the digestive tract are, for whatever reason, moving that gas along more slowly than usual. But researchers have also found that some people experience the sensation of bloating with no detectable change in the actual amount of gas in their abdomen at all, which suggests that the muscles surrounding the gut and the nerves reporting on their state are simply more reactive in some people than in others, registering ordinary digestive activity as an uncomfortable pressure. It's a reminder that a sensation as simple as fullness is, like so much of digestion, not a direct readout of physical reality, but an interpretation, assembled by a nervous system that is sometimes more sensitive than the situation strictly calls for. Constipation and diarrhea sit at opposite ends of a single spectrum, both describing not really the presence or absence of any particular substance, but the speed at which the large intestine is doing its job of reclaiming water from waste. The colon, moving material along slowly, gradually pulls water out of it, and the longer that material lingers, the more water gets withdrawn, until what remains becomes hard and difficult to move. This can happen for reasons as simple as not drinking enough water or eating too little fiber, since fiber, moving largely undigested through the gut, provides bulk that helps the intestinal muscles grip and push effectively, the way a fully loaded conveyor belt moves more predictably than an empty one. Stress, certain medications, and even something as mundane as a change in routine, like travel, can slow this transit as well, because the nerves governing intestinal movement are, as established, deeply entangled with the nervous system's broader state. Diarrhea runs in the opposite direction, arising when material moves through the colon too quickly for water to be properly reabsorbed, or when the intestinal lining, often in response to infection, actively secretes extra fluid into the gut rather than absorbing it. This is, in fact, a defense mechanism as much as it's a malfunction, since a body invaded by certain bacteria or viruses can benefit from flushing them out quickly, and the diarrhea that follows a stomach bug, however unpleasant, represents the intestine doing exactly what it's supposed to do under the circumstances, moving quickly to clear a threat rather than allowing it to linger and multiply. This is also why the discomfort of diarrhea is so often accompanied by cramping, since the same wave-like contractions that move food along under normal circumstances become stronger and more urgent when the body is trying to expel something as fast as possible. Ulcers tell a different kind of story, one that took the medical world by surprise when it was finally understood. For much of the 20th century, doctors assumed that stomach ulcers, those painful erosions in the lining of the stomach or the upper part of the small intestine, were caused primarily by stress and diet, by too much acid produced by an anxious, overworked digestive system. It wasn't until the 1980s that two Australian researchers, Barry Marshall and Robin Warren, proposed something far stranger, that many ulcers were actually caused by a bacterium, Helicobacter pylori, capable of surviving in the harsh acidic environment of the stomach by burrowing into the protective mucus layer and neutralizing the acid immediately around it. The idea was met with considerable skepticism, since a bacterium thriving in stomach acid seemed almost as implausible as a fish thriving in a bonfire, and Marshall, in a rather dramatic demonstration of the confidence he had in his own findings, eventually drank a solution containing the bacteria himself and developed gastritis as a direct result, offering some of the most convincing evidence for his theory. The two researchers were awarded the Nobel Prize years later, and the discovery transformed ulcer treatment from a matter of chronic acid management into something that could, in many cases, be resolved with a course of antibiotics. A reminder that even a body as thoroughly studied as the human digestive system can still hold on to genuine surprises. Food intolerances and food allergies, though often spoken of interchangeably, describe two quite different mechanisms. An intolerance, like the lactose intolerance that affects a majority of the world's adult population, usually reflects a simple absence or shortage of a particular digestive enzyme, in that case lactase, the enzyme responsible for breaking down the sugar found in milk. Without enough of it, lactose passes undigested into the large intestine, where resident bacteria ferment it eagerly, producing gas and drawing water into the colon, which is why the consequences tend to be uncomfortable rather than dangerous, a matter of bloating and looser stools rather than any risk to life. A true food allergy operates through an entirely different system, the immune system, which mistakenly identifies a harmless food protein as a threat and mounts a defensive response against it, sometimes a response severe enough to affect breathing or blood pressure throughout the whole body, not just the digestive tract. This is why a peanut allergy and a lactose intolerance, despite both being commonly described as food sensitivities, belong to fundamentally different categories of biology, one rooted in a missing enzyme and the other in a case of mistaken identity by the immune system. Reflux, the sensation known more familiarly as heartburn, returns to a theme touched on earlier, the muscular ring at the base of the esophagus that's supposed to stay closed except when food is actively passing through it. When that muscle relaxes at the wrong moments, acidic stomach contents rise back up into the esophagus, whose lining, unlike the stomach's, has no thick protective coat of mucus to shield it from such an acidic encounter, and the resulting irritation is what produces that familiar burning sensation behind the breastbone. Certain foods, certain postures, and simply lying down too soon after eating can all make this relaxation more likely, which is part of why the discomfort so often makes its appearance at night, when gravity is no longer helping to keep stomach contents where they belong. Inflammation, in its broadest sense, threads through many of these conditions as a kind of common undercurrent, the body's attempt to contain and repair irritation or injury wherever it occurs along this long internal passage. In small, temporary doses, it's protective, but when it persists longer than it should, the very response meant to defend the tissue can begin to damage it instead, a distinction that separates a passing stomach upset from something that unfolds over months or years. Let's let that thought settle for a moment, the way inflammation itself often does, quietly, without announcing itself, before we gather up everything this long night has carried us through and let it rest into a single, slow unfolding. Think back, if you'd like, though there's no need to strain for the details, to where this journey actually began. Not in the stomach, not even at the mouth, but somewhere just before that, in the moment a smell drifted past and the mouth began to water without any conscious decision to do so. That response has a name, if names matter to you right now, or you can let it drift past unnamed. Some physiologists call it the cephalic phase, the head's own contribution to digestion, a kind of anticipatory hum that starts before the first bite ever touches the tongue. It's the same reflex a person feels standing near a kitchen where bread is baking, or lifting the lid off a pot on the stove, that sudden readiness in the mouth that arrives uninvited. That anticipation, that quiet readiness, was the digestive system already at work before a single bite had been taken, saliva gathering, enzymes waiting, the whole arrangement primed like a kitchen with the lights already on, the burners warm, the utensils laid out, everything prepared for a meal that hadn't technically started yet. Then came the teeth, grinding and tearing in that peculiar cooperative motion unique to mammals, molars built for crushing where other creatures, a shark, say, or a snake, might have only points for piercing or swallowing whole. Every bite broke food down into smaller and smaller fragments, increasing the surface area available for the chemistry that was still to come, the way splitting a log into kindling lets a fire catch faster than a single solid piece of wood ever could. Saliva did more than moisten. It carried an enzyme suited to starting the breakdown of starches right there in the mouth, so that a piece of bread, chewed slowly enough, patiently enough, might begin to taste faintly sweet before it was ever swallowed, the long chains of starch already being coaxed apart into sugars small enough for the tongue to notice. It's a small, almost overlooked detail of the whole system that the very first taste of sweetness in a slice of bread isn't really about the bread at all, but about how long it's been sitting in the mouth. And then the swallow itself, that small miracle of timing, the soft palate lifting to seal off the nasal passage, the airway closing over so that food could pass safely down the throat without straying into the lungs, all of it happening in under a second, more times in a single day, several hundred at least, than most people ever pause to count. The esophagus took over from there, not simply a chute obeying gravity, but a muscular tube performing its own rhythmic squeeze, a wave of contraction called peristalsis moving steadily downward, meaning a person could, in principle, swallow while lying flat or even upside down, an astronaut floating in orbit, and the food would still make its way down, carried by muscle rather than by falling, the body never actually depending on gravity for this part of the journey at all. The stomach received it into an environment stranger than almost anywhere else in the body, an acidity sharp enough to dissolve metal, sharp enough that if a drop of it landed on a countertop it would leave a mark, and yet the stomach lining survives this every day because of its own thick coat of protective mucus. A barrier renewed constantly, replaced faster than the acid can wear it away, the cells beneath it turning over and rebuilding themselves every few days, an entire lining quietly replacing itself while its owner goes about an ordinary life, unaware. Inside that churning acidic chamber, proteins began to unfold, their careful three-dimensional shapes loosening under the assault of acid and enzyme alike, the way a tightly folded piece of paper loosens and opens when left out in the rain, work that had to happen before those proteins could ever be broken down further into the smaller pieces the body actually needed. The stomach didn't rush this. It held food back, releasing it gradually into the small intestine in careful portions, a slow, metered trickle rather than a flood, because what came next required patience, and patience, it turns out, is something the body practices constantly, even in organs that never make the news for it. The small intestine, that impossibly long and improbably folded tube somewhere near 20 feet if you could stretch it out straight, tucked more surface area into the abdomen than most people would ever guess, its walls textured with folds upon folds, and each of those folds covered in finger-like projections called villi, and each of those villi covered in still smaller hair-like structures called microvilli, until the total absorptive surface, if somehow unrolled and flattened, would cover an area closer to a tennis court than to anything one might picture fitting inside a human body, all of it folded and refolded and tucked away so efficiently that it fits, quietly, inside a cavity smaller than a suitcase. It was here that the real chemistry happened. Bile from the liver, stored and concentrated in the gallbladder until it was needed, breaking large fat globules into smaller droplets the way a bit of dish soap breaks apart grease in water, spreading it into a fine film rather than a slick, stubborn layer. Enzymes from the pancreas arrived in a steady, precisely calibrated stream to finish the work the stomach had started. Carbohydrates reduced to simple sugars, proteins reduced to their component amino acids, fats reduced to fragments small enough to be absorbed. And all of it, every nutrient the body meant to keep, crossed through that vast folded landscape into the bloodstream, carried away toward the liver first, that quiet chemical checkpoint sorting and processing what arrived, and from there outward to fuel every cell in a body that had no other way of getting what it needed except through this quiet, continuous act of digestion. No shortcuts, no exceptions, every meal ever eaten following this same unhurried path. What was left moved onward into the large intestine, and here the story took an unexpected turn, because what continued the work at that point wasn't the body's own tissue at all, but trillions of microorganisms, an entire hidden population living within, more individual cells by some estimates than the body itself is made of, each with its own preferences and its own chemistry, breaking down fibers the human body had no enzymes of its own to handle, doing quietly for us what we simply cannot do for ourselves. In exchange for a home and a steady supply of food, these microbes produced compounds that nourished the very cells lining the colon, short-chain fatty acids among them, and perhaps, if the evidence continues to hold up under closer study, influenced far more than digestion alone, mood, immunity, and metabolism among the possibilities still being carefully investigated rather than settled, a field so young that much of what's known today would have sounded like speculation only a generation ago. The large intestine, meanwhile, drew back the water that had been used throughout this whole process, reclaiming it so the body wouldn't lose it, gradually transforming a watery residue into something firmer, the way a wrung-out cloth changes shape and weight as the water leaves it, until at last what remained was ready to leave the body entirely, the final and unglamorous but entirely necessary conclusion to a process that began, hours or even a day or more earlier, with nothing more than the smell of food and a mouth beginning to water. And running behind all of it, silent and unceasing, was the enteric nervous system, that vast web of neurons woven into the gut itself, hundreds of millions of them, more than exist in the spinal cord, sometimes described, not entirely without reason, as a second brain, capable of coordinating so much of this contraction and secretion and movement without waiting for instructions from the brain in the skull at all. Cut the connection between the two, as has been studied in certain circumstances, and the gut keeps working, keeps its own rhythm, its own quiet intelligence intact. The two brains stayed in conversation nonetheless, signals passing constantly along the vagus nerve in both directions, the vast majority of that traffic actually running upward, from gut to brain, rather than the other way around, which is part of why a nervous stomach and a nervous mind so often arrive together, and why calm, when it settles into the body, tends to settle into digestion too. All of this, every fold and enzyme and muscular ripple, every microbe and every quiet electrical signal traveling along the vagus nerve, has been happening within you tonight, whether or not you were paying it any attention. It doesn't need your attention. It has never needed your attention. It has been running quietly since long before you learned to read, since before you had words for any of it. This entire, elaborate, and ancient system, older than language, older than fire, doing its unhurried work while you did other things, while you slept, while you are sleeping now. So let your attention come back, gently, to something far simpler than any of this. Just your breathing. In, slow and unhurried, and out, slower still, the chest rising just slightly, the shoulders softening a little more with each exhale. There's nothing to do with this breath except let it happen, the way digestion happens, the way the heart beats, the way the whole body simply continues, faithfully, without needing permission or effort from you. Feel the weight of the body sinking a little further into whatever is holding it, the mattress, the pillow, the quiet dark around you. The stomach is at rest now, or nearly so, the intestines carrying on their slow, patient work at their own unhurried pace, the whole long system simply continuing, the way a river continues, without any need for you to watch it. There is nothing left to explain tonight, nothing left to figure out, no next fact waiting to be delivered. Just this breath, and the one after it, and the soft, ordinary miracle of a body that keeps working through the night without asking anything of you at all. Let your mind go quiet along with it. Let the thoughts loosen and drift the way food drifts through that long, unseen passage, slowly, without urgency, toward wherever they're meant to settle. There's nowhere else you need to be right now, and nothing else you need to understand, just this breath, and this one, and the soft, steady dark. Rest well.